Now let's take a look at these projections, and let's start right at the beginning. Suppose we want to project one vector onto another. So we have some W, or rather a vector in n-dimensional space. We want to project it onto a vector A. What that means is we want to write the W as a sum of an x and a y, so that the y is orthogonal to A and the x is parallel to A. If we write that out, then we want this x to be k times A, and we want the inner product between A and y to be 0, and W is the sum of the two. And from that, it's easy enough to see that if we that the only solution for x is to have for k is to have k to be inner product between W and A divided by the norm of A squared. And you can see this simply by taking the inner product of A with this expression here. So A inner product, or W inner product A is this term inner product A. This goes away, and you're left with x inner product A, which is the norm of A squared times k. And so we have this the solution here, where in a special case where the length of A is 1, it's a unit vector, we have simply k equal to the inner product between W and A. And this technique is used in the Gram Schmidt process to build a sequence of orthonormal vectors, unit vectors, which are all orthogonal to each other, and that they span the same space as a starting collection. So let's take a look at how this is done. We take a look at the first vector, and that's simply we started with an A1. Let U1 span the same space as A1 simply by taking A1 and divide by the norm, the length. Then U1 has length 1, and it spans exactly the same space as A1. Next, for the second vector, what we're going to do is we're going to project the second vector onto U1 and take the residual from that. So here's the projection onto the first one, and then we take the difference, and then we scale that to have length 1. Since it is a projection, we know that this residual is orthogonal, and then we have an orthogonal vector, then we have a unit vector which is orthogonal to the first U1. And now you continue doing the same. So you project onto the first two, and here it's useful to realize that when you're projecting onto a space spanned by two vectors, that's if they're orthogonal and unit vectors, it's enough to project onto each one separately. And again, that's easy enough to see because of the orthogonality properties. Now, if these collections this collection starts out as being independent, so they span a p-dimensional space, then you will end up with p of these. Now, if, however, they are dependent, then you only end up with r of these p's, and r is going to be less than p. What happens in the case of dependency is that one of these residuals will be 0 and will then be omitted. So what we have now is we have a basis for the same span as these initial A's, and what we can do next is we can expand it to a span for all of Rn, and the simplest way to do that is simply to say, instead of just considering the first A's, the PA's, we can add on to that all of the unit vectors. This is the EI is the unit vector which is all zeros except I in the ith place, and then use Gram Schmidt on this set here. And of course, these are too many. These are n plus p vectors. So as you go through this sequence, some of the residuals will become 0 and will be dropped. But we will end up with n vectors which span all of Rn, and the first r of them span exactly the same space as the starting vectors. So this is the obvious way to come up with a new basis for Rn, which spans first the span of X and then the remainder of the space. So we can then write both X beta hat in terms of these U's, and then you can also write Y in terms of these U's. And this is extremely useful. We're going to use that quite a bit and get back to the properties of these coefficients later on.